Okay, so let's say you wanted to control a reactor. This is a reactor. There is a feed in. Okay, there is a product out. Okay, and there may be a stirrer inside, and you may be putting a heated. So this may be jacketed, and jacket would have a heating fluid or cooling fluid, which would be recirculated by means of a pump, so on and so forth. And you are charging some feed and taking out, I'll say Fi and Fo, which is the feeding and feed product in. There could be multiple feeds also. Let's say this is F1 and this F2. You are adding both and do some mixing, whatever, and or some reaction happening, and you are taking the product out. So mostly, as I told, feedback controller would act on the evidence. So which essentially means that, let's say your final product is F naught, and you have F naught with some specifications. So the specification is your product, the distinguishing factor of this product. You need to have the specification to be met so that it could be sold. This could be anything. If, let's say if you are looking for a vaccine, so you need to make sure that it satisfies all the FDA regulations to some extent. So of course they are not continuous manufacturing; they are mostly batch manufacturing. So this is a continuous manufacturing example, is what we told. So you might have heard that if many of these critical quality controls are not satisfied, you have to throw the product. It would be discarded outrightly. So you do some measurement of the product. So most likely, if it is a pharma product, so there could be many type of products. Right? Most likely, if you are a pharma, petroleum, then pigments, anything. So the governing fact here would be the composition. So you have to check whether the outlet product has good composition. So you'll have to have an analyzer. So the analyzer would analyze what is the product composition. Okay. And this would go to a controller. So this is an instrument. So analyzer is a virtual instrument or a sensor, I will call. The sensor would give some indication regarding this is the current output. Then it goes to a controller. So I'll say a CC, composition controller. Okay. So what is a controller? Controller either could be a soft controller or other could be a hard controller. See, we are talking about instrumentation here. See, so we are going to, so this is now slightly away from our chemical engineering domain. So which essentially means that you are talking about sensors, signals. So one option is to use a controller which is hard, which essentially means that it is a circuit board. It can be a chip, it can be a circuit board which works based on certain actions, which essentially means that, or it can be a soft controller. Soft controller means that there may be some central PC, which in process control context is called as DCS, distributed control system, uh, which is having high level of compute where you code in this control algorithm. So you in the soft means that your control algorithm. So you are just coding an algorithm in a PC. You should not call it PC. You should call it as a computing machine. CM. So this could be PC for a smaller case. It could be larger case. It could be a distributed control system or hardware controller, which means that you buy it. You can buy certain controller structure which has been hard coded by means of wires. So in that case, it would come in here, and this they would do some calculation and send it back. So this okay. So now here, this is your physical variable, and from this point onwards, generally a sensor analyzer would So this is a physical line that going into sensor. This is a physical line. From here onwards, it would be signals, because the sensor would convert what you call your physical variable into corresponding electrical signal. If it is an electrical transducer, it could be it may or be a pneumatic signal if the sensor is other way around. And of course, this signal is going to your controller, and controller would do various manipulations if you, and do the output of the controller, so that way. So see, what the main aim of the controller is to minimize target spec, which you really know what you need to sell outside, and the current spec, which is measured by the sensor. So you minimize this, whatever way of minimization we can think. It could be simple minimization, square, or something else, just an error, whatever. Whatever be the demanded way. So once that is done, okay, this TCS would give some signal back to the composition controller. Okay, now composition controller again. So this is all electrical signal. So it might give you some level of signal here back. You do all manipulation. If the signal is high, for instance, you need to have a reduced voltage. They might put a what you call resistance to drop the voltage, or you decrease the resistance so that the current flow is high. What so that hardware part is done. Then this electrical signal would go to most likely go to something known as I to P, which is generally known as current to pressure transducer. Current, I stands for current, P stands for pressure. Why? Because eventually you would control F1 or F2. Let's assume that we are controlling F2 in this context. Okay, you need a valve. And most of the valve, the way to control the valve is by means of pneumatic air, because there will come there. So this I2P converter would correspondingly convert the current signal into pneumatic signal. So there would be instrument air is something that would come. It is called instrument air, which essentially means that there would be a lab. So if you go to physical plant or even the process control lab, you come and see there may be a huge compressor which is working, and the compressor lines would be going everywhere. So this huge compressors would supply instrument air. The instrument air here also would be, there would be a line of instrument air and the current signal. Then that would give you what is the air that you need to be air signal what you need, or pneumatic signal that you need to be taken to open or close the valve. Okay, and let's say this is the valve diaphragm, and what would happen is when air supplies, there are two types of valves specifically: air to close and air to open. So eventually this control valves would be like this. There would be a stem. This is called the stem of the control valve. This is the line and this is the plug. This plug either would obstruct the flow, or when it moved up, it would completely make the free flow. And this is the diaphragm. And there would be a diaphragm here. And the air line, diaphragm would be generally an elastic material that can compress. This is diaphragm. This is plug. So the instrument air line may be coming from somewhere here, and may be connected over here. So let's say, and this is the airline. and you are supplying air on this top part of the diaphragm. So can you say this valve would be air to close or air to open? Can someone say? Which category it would belong? You have a diaphragm and you are supplying the air on the top of the diaphragm. Anyone? Am I audible to all of you?
Sir, air to open.
Hello? Am I audible? Is there
Yes,
some
sir.
problem?
So yes, sir, you're audible.
Hello?
Yes, sir, you are audible.
So tell me, this is if this sort of a geometry would be air to close or air to open? Hello? Is there some problem? Is there any problem in terms of my voice? Hello? Hi guys, are you guys around? Am I hello?
Yes,
Hello.
sir, you're audible. Hello.
That's fine. I think so. So I would just kind of miss that. Okay, so considering the texture, air to the top of the diaphragm, this would be air to close or air to open.
Sir, air to open.
Why do you say that? So okay, so I'm giving you two options. Huh?
Mhm.
So let me just give you. So I am having an air line and I am connecting here. So this is also A. So this is option A. Sorry, let me also get the right color. This is option A and this is option B. So which one of this can be air to open or which one of this can be air to close? Just by naive understanding. I'm not asking anything. Like you can just look at this diagram and what do you think?
Sir, B will be air to open and A will be air to close.
Perfect. So what it happens? So you supply air to the diaphragm. The diaphragm would just lift up. So this is they have named it just like that. What happened once the diaphragm would be lifted up, the stem would move up and there would be flow. And in the other case, you would supply the air. Huh? So what would happen? Your diaphragm would come, okay, come down and it would close. And there is also another class, or in fact, another uh, parlance in the same domain. So one is normally open, another one is normally closed. Okay, so so which so what do you mean by so one of this would be normally open? Which case is normally open? Hello. Normally open that in general it is open and you need to act on it to make it close. So are you all with me? Hello. Anyway, I'm moving ahead. So normally open essentially means that you need to supply air to close it because it is normally open. So this is A and this is B. So why I am saying this, let's say you are working in industry. So these are industry specifications. So like manufacturing specification, which is generally approved by ISA, Instrumentation Society of America. So that's kind of, it's like FDA kind of a business. So they have their own standards, which I think is widely used everywhere. So let's say you are designing, so one of you have given the job to design a controller, and you would start with identifying, okay, what is the analyzer, what is the transmitter, then you will also take a look, what is the I to P range you want, then you come to the control bar. So see, you have to buy this all from market. So when you go to a vendor in the market, he doesn't know what is. He will just ask, which valve do you want? So you have to say either air to close or air to open, or normally closed or normally open. Sometimes you might get only normally open valve. So you will have to engineer in such a way that your airflow is good enough to control that. So, and there are safety critical applications that requires lines to be normally open or closed. For instance, let's say you are working with a line that is containing corroding liquids, corrosive liquids. So which valve do you buy in the market? Let's say you are given the stuff.
Sir, we'll buy a normally closed type of.
Perfect. So what could be the reason for that?
Sir, because the liquid that is given to us is corrosive, so we don't want that it is flowing continuously because it can damage the pipeline.
Okay, so basically you will have to look for fail-safe conditions, right? So let's say your compressor got tripped. Fine. And what happened? So your air supply is gone here. So compressor trip would result in cutting the air supply. Okay. So and which essentially means that many of your plant would be affected by that. So you really don't want any of the corrosive materials to be sent into the downstream, so that you would reduce the chance of unsafe conditions. So you would buy normally closed. But why normally closed? If the air, so if there is no air in the compressor, it would, your stem would come and become automatically closed and just plug that line. Fine. And there will be other cases. So you can figure out an alternate case. So you can also have a case when normally open. For instance, if it is a water line, so water or there are material that you would tend to always want to circulate in such a way that, let's say, if you hold them together for a long time, it would solidify. So for instance, materials like slag, waxy material. So you have this line. Just give me, I think my screen sharing has a problem. Let me reshare my screen. Okay, you can see my screen, right? Some delay. Is there any delay? Hello? Could you see my screen? Can someone
Yes,
say?
yes.
You can see, very good. Absolutely fine. So let's say you are using materials like waxy liquid. For instance, slag, which essentially means that if you keep them in the line will solidify. Then there is no way you will have to kind of cut down the whole pipeline if it is got solidified. So in those cases, you would open for normally open. So you only close it if your requirement comes in. Otherwise, there should be always a circulation needed, so that it won't make any unsafe condition. So okay, so based on that you have fixed this control valve, and this current would give this I2P converter would give the signal to the control valve, and this instrument air is also giving a connection here, and based on this both signals it would either open or close the valve so that the flow can be regulated. So this is a typical feedback control what you call. Hello. So now our question here is, how do you design this guy, which is the controller? Because you need to have a logic, right? So because see, you are seeing this, it is first of all signals. Your original variable is physical. So the original variable, your sensor convert into signals. Then go to the controller. That is also signal. Fine. The controller is communicating to I2P. That is also signal. But the difference here is that this is most likely electric and this is pneumatic. And your controller is trying to minimize the error between actual what you call process that is desired, not and the desired product. So Y means that assume that it is specification, and actual and Y desired. So there is a lot of conversion happening from original variable, which is then it goes to the sensor. So when it goes to the sensor, generally the standard is between 4 to 20 milliamperes. So that is the most sensor output, or 1 to 5 volt, in whichever specification it is. So, and you don't have a control when you go into the market, and the vendor would say this is the specification. So if you don't want a 1 to 5 volt, you will have to look for. So these are the two specification, one in terms of voltage and one in terms of current. So you have to buy your sensor suitably, and these are all electrical signals up till here. So this I2P convert them into 3 to 15 psig. So because it is air pressure. So this is the industry standard. So you see here it is 3 to 5, and this 3 to 5 is operating on your control valve. Okay, and to control your original variable. So there is lot of jugglery. So your original variable may be temperature, which may be varying from 300 to 400 Kelvin. Fine. But all other inside transformation is in terms of the industry standard. Even let's say your what you call your operating range is between 500 to 1000 Kelvin. So this will only happen in this layer, your first layer. So here from the second layer, which is from sensor to I2P, this is all industry standard. Industry standard means that it is all fixed. You don't have any control. You have to buy those components that gives you within that range. So sometimes your sensor will not be able to measure what you call 1000 Kelvin, because the sensor range will be different. Or so you will have to go and buy those sensor that gives you the range. So it measures 500 to 1000 Kelvin and produces a signal worth 1.5, 1 to 5 volt or 4 to 20 milliamps here. So this is the sensor that you would buy in that context. Let's say if you want to operate between 300 to 400, so you will not use that temperature sensor. So the temperature sensor can be either, so let's say it is temperature. So mostly used sensors are RTD, which is resistant temperature detector or device, whatever you call, or other one is thermocouple. Okay, and if it is pressure, most likely it would be gauges, which essentially means that Bourdon gauge and so on and so forth, or which is other one is DPT, which is known as differential pressure transmitter. So they will all give the operation, what you call the outlet. So they would take, so you will have to read a sensor data sheet, and the data sheet would give you. So let's say category 1 will be good for 400 to 500 Kelvin, and category 2 would be between. So the whole range of temperature of whichever do you need to operate, it is available as a data sheet to the vendor, and you or the company that makes the RTD, you'll have to go back and check. Okay, so you need this, and you say that specification to the market, and they would buy and get you. Otherwise, if you just need 300 Kelvin, and they might not understand, because see, these are all done by sellers, right? So they are not really interested in terms of learning the technical specification. They will only sell you, tell a specification, they'll give you the product. So the point what I am trying to say is, except the first level and the last level, which is again the flow. So everything inside is perfectly standardized according to the industry, most likely done by ISA, Instrumentation Society of America, or International Society of Automation. Both are called ISA. So they have a series of standards which everyone in the world will have to, or rather they have been standardized across every world. Why? Because let's say you as an engineer work in India, let's say you are going to go and work in, let's say, in Middle East or in USA, you cannot change the standards, right? So you need to have a seamless connectivity of whatever you are using there and whatever you are going to use. And also, see, this many of this manufacturers, they are they are making the same product. So let's say if you wanted to, all the standards across the country were different. So one of the bigger sensor companies, so who makes sensors like for Marshall, so they would need to make separate sensors for India, separate sensors for China, so or USA, wherever, to avoid that confusion. All this. So once you are inside the automation loop, all the process have been standardized, and you have to use the standards, and these standards have to be later vetted. Okay, then it comes to quality compliance. You might have heard about ISO 9001, 4000, and things like that, which essentially check whether these standards have been quality control proof. So that's the way industry works. So you cannot arbitrarily change anything. It can, of course, you could do it in your lab, but in a large scale industry, it is not possible. You will have to strictly obey the international, what you call, internationally accepted standards. And they have that host, which has to be quality control, which is basically your ISO, and things like that, 9001, 4000, 8000. So there are various standards. So unless you don't do this, if you are, let's say, working in a company or you are opening in an industry, your industry would not have this quality control standards. And what is the problem if you don't have this quality control standards? Okay, you are selling a product. Let's say you wanted to sell your F2 to somebody in US. You are making your industry is situated in India, and you are what you call, you are selling into a client in the US. First thing that you would ask, which all standards you are following. You say that, okay, I don't have an ISO standard because I have not fulfilled to these kind of things. Then he'll say, I don't want to buy it from you. What is the guarantee that your product would have credibility. So this has become a very, very, very stringent operational exercise, starting from the design phase to the implementation phase, so that everything is extremely standardized. So why this is done? Of course, for seamless transformation. For instance, if let's say one of your flow control valve has been malfunctioned, you don't have to hunt in the market to get what I will fix, because it's all standardized. Now you just you only have to name the standard, come and fix. Even the line's diameter is standardized. You see, the control valve with bore diameter, everything is standardized. So it's more of a plug and play. That's why you need to somebody who has been in industry for a long time, they would just speak everything in terms of this what I call standardized numbers. One is of course this seamless transformation. Other one is for quality control. So there is no monkey business. Everything is being used by internationally accepted standards. So that is one aspect. So now let's coming back to where we have stopped. So eventually you need to have the following. This is what I have also told you. You have a sensor. Okay. Then there is a controller. So controller would give the error and it will go to what is known as IPP, current to pressure transducer, and that would communicate to the control valve. So you see that from here, so this is also very standard. It's of course it's a piece of P and ID. So have you heard of something known as P and ID? There are two things, PFD and P and ID. Hello? Hello? Are you guys there?
Yes, sir.
So have you heard of something known as PFD in an industrial perspective and P and ID in an industrial perspective?
No, sir, not yet.
Okay. So PFD is process flow diagram. Okay. P and ID is piping and instrumentation diagram. Piping and instrumentation diagram. So let's say you are making your industry, your own industry, or you. So first thing, so either you. Okay. So have you heard about licensing? Licensing a technology. Head of in. So have you underwent a course on chemical process technology?
No, sir.
Hello, guys. Process technology on making components like methods like H2O for production, ammonia production, so on and so forth. Not yet.
No, sir.
No, sir.
Okay. So let's say you are going to make your own plant. So you have made a venture capital. So you have accumulated a capital and decided to make simple example. You are going to make an ammonia plant. So what is that ammonia production process is called? This is you would have heard a lot.
Sir, Haber process.
Absolutely, Haber's process. So Haber's process is just the ammonia making process. But when you make an ammonia plant, okay, so you need to have reactors. There may be multiple reactors. One for the reaction to happen, one for cleaning, one for scrubbing, so on and so forth. Okay, and there are various steps that helps to complete the Haber's process. Haber's process is just a one element, right? It's like what you call the steering wheel of a car. You need, but steering wheel is not good enough to drive a car. You need to have seats, you need to have tires, you need to have a body, everything. So this whole process, so for instance, you take the feed and you might, so starting from, let's say, you would heat up the feed by means of heat exchanger, then it goes to the reactor, then the reactor would go to a separator, and the separator, no, I'm saying there are many steps. I'm not showing you an example. And this from when you go to the reactor, there may be a recycling stream that is going back to this thing, then that require a recycling pump. And finally, you go to your product. So many industrial giants might have made this large-scale production of Haber's process. Such technology is patented and is available with them. So, for instance, KBR, the one bigger license company, UOP, UOP and Honeywell. So now they are together. Then another one is what you call. There are many. So I don't want to list anything. Even Shell has their technology. So what they are doing is they made this end-to-end production mechanism. End-to-end production mechanism. And patented it. So if you want to make your industry for production of the ammonia, you have two options. One option is you make your own technology. Your own technology and patent it and use it. But when you start, because you learned chemical engineering, you have a very different idea, so you thought this would be possible. Technology in the sense that end to end, starting to the end. How do you do everything? How many pumps do you need? Other thing is you buy from one of these licenses. You have to pay and they would license their technology to you. And when you license this technology, what they would give you is something known as PFD, which is process flow diagram. So which is essentially the same thing. It would start with, and to license the technology, what you will say that you will have to give the specification to them. I need to make, let's say, 1,000 metric ton, what you call ammonia per week or something. So based on that, they would scale the whole equipment and give you the preliminary details. Okay, you need to have the reactor worth size, maybe 1,000 liters, so on and so forth, or whatever. And but that is just a preliminary information, because you see there is nothing, no control, no information. You take you then once you get the PFD, you would hire a detailer. So which is also called as detail engineering firms. So there are many detail engineering firms across. So the nearest detail engineering firm to near IIT Delhi maybe an EIL. EIL is this in Bikaji Kama. So what they does is they take up the PFD from you and come an agreement with you. And also now I'll tell how you want to see. PFD is nothing but a high level. This is a very high level information. You say that this is the of the plant, this would contain this many reactors. So this reactor, I will say reactor 1, this is reactor 2, and this is pump 1, all the details they'll give. Now detailer pick up this information and would give you what is known as detail engineering drawing. There are many aspects of detail engineering drawing. One aspect of that is P&ID. So P&ID, what you do is you map every instrumentation line, piping and instrumentation. All the piping lines and instrumentation lines would be captured in the P&ID. So for instance, let's say this is your reactor, this is your second reactor, and this output, and you have a recycle. This was a simple example, right? You have feed in here, feed out. So this was the PFD. In P and ID, what you would do, whether you need a valve here, that information would come because that is instrumentation. And how do you know the valve is needed? Then you need to know your what is the level of the downstream tank level. So the level will go, then there may be a level controller. The level controller would communicate to the control valve. So all the piping, so this was not part of the PFD. PFD is giving you high level information. So it's up to you to get, sometimes even licenses would give you P and ID. It's up to us what is the contract that you're going to get agreed upon. So why, but PFD is very, very high level. P and ID contain each and every, because this is a piping line, because for measuring the level, you have taken a piping line outside. And instrumentation, there is a level sensor, and also going back over here. So this would be like a very comprehensive information. Okay, so now if you have your P and ID available, you will have, where is your controller is setting. Okay, so once you have that decided, you call a control expert or an APC expert. So help me to design how you want to. P and ID also will not give you any logic. You say that there is a level control is needed to control the level from reactor 1 to reactor 2, whatever way. So this third person who is a control, which is APC, people will call APC expert, he would give you all the detailed control logic. Okay, so now what you are seeing over here is give me a minute. Yeah, so whatever you are seeing here is a snippet of the P and ID. So you see there is instrumentation line, everything. The PFD of this would be excluding all of this. So I'll just cut these lines. So PFD will not have anything. So PFD might even don't have a valve. It'll say that 2 lines coming in, there is a reactor, there's something going out. Okay, so P and ID would contain anything, and it will also show the signals. You see, so this is very, very important. So it's important that you should be able to read a P and ID. So AT means that A is generally a notation for analyzer, T is a notation for transmitter, analyzer, transmitter. So this is a continuous line. From here, it happened to be dashed, which is an indication of electrical signal. Okay, controller is also in hardware or software. So from there also it is electrical signal. But from I to P, because I to P is converting current to pressure. So then that air pressure is going and opening your valve. Okay. Then the signal suddenly changes from electrical signal to the pneumatic signal. So pneumatic signal is generally represented by a line with a 2 cuts. It's just to show that it is air line. And so up till here, this is what I told. So here your process variable would be normal. Here also it would be normal. But this portion, everywhere it is fully standardized. The variable that you would always see is either it can be 4 to 20 milliampere current signal, 1 to 5 volts electrical signal, or 4 to 3 to so okay, I think I told 3 to 15. I think so. I'm not really sure. I think 3 to 5 psig or 3 to 15 psig, but I will double check. My understanding was that it is 3 to 15 psig. But anyway, so as an engineer, it's very easy for you to work because they are all standardized. And as you told, this would also help to avoid any haphazard, what you call, issues, because you are using a global standard and which is vetted by quality control. It is 3 to 15 psig only, I think. So you don't need to worry. Okay, so now coming back to the controller. So now what are we going to do? We are going to zoom in this guy. And how do you design this? So next 4 chapters or 4 or 5 modules will focus fully on how to design controller under various contexts. Okay, so now coming to the controller. Okay, what a controller controller takes an input signal and it would have a set point, which is the target value. So let's say if you need to have a specification So your output product will have a specification. That specification is fed inside the controller. And what it does is it also takes the current value and calculate the error, and based on the error it gives you a logical output that is good enough to trigger your airline, so that what you call control valves can be operated. So the simplest case, okay, so what is that your controller is basically working on an error which is working based on y actual. In fact, the error is generally calculated by y desired minus y actual, because your controller aim is to just minimize this, right, whatever be the case. So your error should be in such a way that you should move close to the desired value from the actual value. The simplest way to achieve that is by means of adding a proportional value to the error. Okay, so that is what is known as the proportional controller. So proportional controller, so say controller output, you see this is a controller output, this P. You need to define how P should be. So P could be proportional to the error. So what essentially means that a controller output would be more when the error is more. So it would drive, why more? So when it drives more, which essentially means that your valve would be either fully open or closed. You will have to fix that direction by means of looking valve, which is based on what is known whether it is air to close or air to open. You will have to design the logic. You need to put a negative sign sometimes. You might need to put a negative sign depending upon whatever may be. So here the simple assumption is that my controller output is of course proportional to the error. The simple logic is that if the error is more, I will act more. What is the action? Whether it is opening or closing would be detected by the sign of clicking. Why? If it is a, because this is again your customer. What is your customer? Everybody will have a customer. No? A controller customer is final control element or the control valve. So the receiver from the controller, of course, go to I2P though, but eventually it goes to the control valve. So you'll have to check what type of control valve you have kept there, because you might have kept air to open or air to close, depending upon whatever you have bought from your market. You will have to identify the sign, whether I should open or close by means of the sign. But the simple logic, what we are trying to say, that if the error is more, you act more, which is a very fair okay. So what is this? But again, this is also so this is one of the oldest and probably the simplest method. Two things: oldest and simplest. So there are some issues over here. Okay, one. So let's look at what is this proportional control all about. Then we'll see what is the problem. So the controller gain is adjusted to make the controller output changes. The sign of the KC can be chosen, can be to make the controller output increase or decrease. And there is also a term known as bias. So sometimes you need to have, so this control valve, you see, this control valve, no? Sometimes you need to have a threshold apply for air to open. It's like a it's called as sticky phenomenon. It's like you have heard about this big farm plastic fluid and things like that. You need to apply sufficient stress to initiate the flow. The same way you need to have a threshold air supply so that it would start opening. So let's say So of course, we will talk about that also later. There are various types of control valve, which is also called as quick opening. Quick opening, linear and equal percentage, which essentially means that, so let's say, so some of this control valve, you need to apply some level of threshold air so that it would start opening. This opening could be either linear in terms of your air versus output. Okay, it could be equal percentage and quick opening. Quick opening means that for a smaller change of air, there would be a larger output and what you call equal percentage would go other way around. So there are three cases which we will of course learn and suppose. But what I am trying to say, you probably need to apply sufficiently. So otherwise, what would happen? So this is also a safety feature. Correct. Why? Because if there is no sufficient, if you are not putting this condition, for any small variation in the error, your valve should keep on open and close. If there is a minute change in the air pressure, your valve would start opening. That would become a very huge disturbance, followed by a so see this valve head, right? So it is fixed over here. This is metal, most likely a metal. And there is a diaphragm, as we told, no? This diaphragm. So unnecessary movements of this mechanical parts, right, be it a diaphragm or this valve, will lead to erosion, and which is a huge maintenance work. Once if the head is kind of eroded, you will have to change the valve. So most of the time you need to have a threshold airflow to open it, which is kind of captured by means of this biostat. Sometimes if you have, sometimes you don't have. It all depends upon the thing that you buy from the market. And what you see, the controller output is 0 when the error is 0. That is the key aspect. Or if controller output equals to P bar, so which essentially means that it's at the threshold stress. It's not open or closed. It's at that point. So when the error is 0, this whole term cancels out. It would go back to the threshold point. So anything beyond that, it would keep on operating. So this in proportional controller, everything is dictated by this Kc because it is Kc times Et, right? So Kc is the key driver of the controller. Okay, and sometimes it is represented as 100 by Kc, which is called as proportional band. And what would happen? So you see that because of the error, the P bar is its nominal value. The P bar could increase because K times E. Based on the negative condition, if E become a negative by modulus, it would come down. So it would keep on oscillating between this line. This is the error versus P value, while this point would be your P bar. So what is the problem now? So there is no limit, right? So if the error is very large, it would keep on increasing. And what would happen? Your control valve eventually start to hit. It would keep on hitting. Sometimes it would also start putting pressurizing on the diaphragm unwantedly, because error is, you have just kept error. So if the error is very, very high, it would keep on hitting at the boundary. So to avoid that, and so this would again result in tearing the diaphragm. To avoid that, what people tend to do is they clip the output of the controller at certain limits, which is Tmax and Tmin, so that it will operate only in this range. This is just to avoid the stress on the diaphragm. So you don't pressurize. I'll say that now there is no more control output beyond this is constant, so that you would the pressure on the diaphragm would be constant. Okay, so I will stop here and we'll continue the remaining part of the controllers in the next class. It's very close to 11, and I request all of you to be a bit more interactive so that I can I don't have to do this monologue anymore. Any questions? Any questions? Are you all there?
Yes, sir.
Yes, sir.
Okay, guys. So I don't know. I'm not holding you. So 11, it's past 11, and see you in the Friday class. Bye.
Thank you, sir.